All right, so we're going to write equations of tangent lines or lines, however many there are, to this curve when y equals 1. It's got x's and y's mixed together. It's not y as a function of x. So we're going to use implicit differentiation. And the first thing you want to do, to write an equation of a tangent line or any line, you need a point and a slope. So the first thing we want are those points of tangency. So you want to ask, what do we know? We know we want them where y equals 1. So you just sub that in and find those points. Plug 1 in for y, we just get 4x minus 5. When you plug in 1 for y, equals 0. It factors nicely. Somebody did a nice job setting up this problem to work really nicely. If you're watching from home and you weren't in the room, you missed the fact that I screwed it up the first time and made a problem that didn't work very well. So anyway, plus 5 minus 1. That gets us the 4x in the middle. Looks good. And we get x values of what, 1 and negative 5. So we have 2 points here that we're looking at. We're looking at 1, 1, and we're looking at negative 5, 1. Now we need the derivative. So we're going to do implicit differentiation, right? We got x's and y's mixed together there. So we're differentiating with respect to x. Differentiate with respect to x. And with respect to x, that x squared, it's just 2x, right? We've got a product rule here, 4x times y. So 4x is my u, so u prime is going to be 4. So 4 times y plus, and then 4x is my u times my v prime. Y is my v, so just y prime, right? Or dy dx, if you want to go full Leibniz on it. And minus 5y cubed, power rule, we're going to do 15y squared. And then again, chain rule, right? The implicit differentiation, so times dy dx. Okay, I don't really want that to mash into that other part, so we'll shrink it a little. And on the other side we have equals 0, of course. All right, now we want to isolate dy dx. I guess you could start plugging in points at this point, but I think it's easier if you isolate dy dx first, especially since we actually have 2 points to plug in. So factor out the dy dx from the 2 terms that have it. So we're going to get a 4x minus 15y squared in parentheses here. Subtract the other 2 terms over to the other side of the equation. Or we could have moved the dy dx terms over if we wanted to. That would have made it so that these were positive. We could still factor out a negative if we want, or multiply by negative 1 over negative 1. Doesn't really matter, though. Just be careful with the negatives, that's all. I'm going to go ahead and multiply by negative 1. So I'll make that 2x plus 4y on top, right, when I divide. And then I'm going to, with this part, I'm just going to multiply it by negative 1, so switch the order of subtraction. So that'll be 15y squared minus 4x. That way I have a lot fewer negatives in my derivative, and I know myself, and I screw up negatives all the time. So this makes less chance for error. So we're going to have 2 tangent lines, 1 for each point. So I'm just going to kind of like do each one separately here. For 1, 1, my slope, m, is going to equal the derivative dy dx when I plug a 1, 1 in, right? So at 1, 1. And what is that? Well, I'm plugging 1, 1 in for x and y in that fraction. So on top I get 2 plus 4. And on the bottom I get 15 minus 4. So what's that? 6 elevenths? I can do math. 6 elevenths is my slope on that first one. Look good? Awesome. And my 11 doesn't look very good. That's better. Okay. And then the other point was negative 5, 1. So here, let's do that one over here. Negative 5, 1. And again, the slope will be dy dx evaluated at negative 5, 1. This is an important notation to know. The Leibniz notation, dy dx with the line next to it, and then like whatever conditions you're plugging into that derivative. That shows the derivative at that point. Plug in -5 for x, 1 for y. So we're going to get what? -10 plus 4 on top. On the bottom, we're going to get, oh, geez. Oh, that's the ones for the y. That's not too bad. Okay, 15, and then what's that? Plus 20. Okay, and so it looks like -6 over, is that 35? Yeah. Doesn't reduce. Looks annoying, but we don't really have to do much with it, right? We're just going to write a couple tangent line equations now. And here's what we've got. We've got a slope. On one of them, it's 6/11. On the other, it's -6/35. Am I looking good, guys? You guys agree? Cool. And then we've got points for each of these too, so we can just go straight into point slope form. So over here, this one's going to be y minus y1, which is 1, equals m times x minus x1, which is also 1. Done. If you want to put it in a different form, you can. You do not have to. And then on the other one, we've got the point -5, 1, and the slope -6/35. So we're going to do y minus 1 equals -6/35 x minus -5, so x plus 5. And that's it. Looking good? Awesome. I'm going to go ahead really quick, and I'm going to graph that curve and our two tangent lines and see how we did, see how it looks. So you can see the fun of it. I'm going to use Desmos. Desmos is really handy for this. You can just type those equations right in and they work. So yeah, it's kind of a weird looking graph. Let's see. X squared plus 4xy minus 5y cubed equals 0. That's what the graph looks like. And then look at our tangent lines here again. We got y minus 1 equals negative, oh, sorry. Yeah, no, that's right. Y minus 1 equals 6/11 x minus 1. Let's do that. Whoops, got to get out of the denominator. Pretty tangent up there, right? That's at 1, 1, at the point 1, 1. And then we've got, oh, I got to scroll down in there, don't I? Doesn't want me to. There we go. Y minus 1 equals -6/35 x plus 5. Y minus 1 equals -6/35 x plus 5. And yeah, that's going to show us this other tangent line over here. It's really hard to see because that part of the curve is so flat, but it looks convincing.